All right. Hey, everyone. So yeah, Adam and I will be presenting about some of our recent explorations for AEC and geospatial in the context of glTF. So first for AEC, there's been a lot of interest in the architecture, engineering, and construction space to utilize glTF. So primarily for web visualization or for game engine visualization, these are often very massive models. So we have like power plant models or complex BIM models or linear infrastructure projects. And they consist of millions of objects modeled down to the individual nuts and bolts with a lot of metadata per object. And typically the geometry of the source data is some sort of implicit surface representation, whether that's like a BREP or a CSG. And we can then triangulate that when we convert it to glTF. They also have materials that are typically simple, like albedo colors, maybe some tiled textures. And then really the main difference between this sort of data and some other types of data is the amount of metadata. So every single object might have up to 5 to 20 fields of metadata associated with it. So a door might say like what material it is, whether it's wood or steel or whatever, and then it might have some physical properties to it as well. But in general, it's just a lot of metadata and very complex hierarchies of metadata. And so a lot of the existing formats and tools, so IFC is an existing BIM format, and then there's a bunch of DCC tools like Revit that have these complex data models. So we want to be able to carry that over into glTF, basically losslessly preserve both the class hierarchy and the object hierarchies that are present there. So in terms of glTF, so some of the optimizations we're looking at are mainly how can we reduce the number of draw calls? Because if we have like millions of objects, we don't want to render each of those as a separate draw call. We want to be able to batch them together. So some of the techniques we take advantage of are using vertex colors if we can, and then also just batching primitives into a single primitive, as well as instancing if you have repeat geometry, like if all the doors are the same or all the lights are the same. And then in order to enable batching while still preserving interactivity, we have a concept of feature IDs. So every vertex is going to say what ID it is. And then that allows you to then like hover your mouse over an individual element and then be able to query the metadata associated with it, or to color it differently, or to do all sorts of filtering like the GIF on the bottom. And then on the compression side, we're making use of mesh opt. So that's really good for us because it's not just compressing the vertex attributes, but can also be used to compress the instanced data, so the rotation, scale, and translations of the instances. In mesh opt, since it applies to buffer views, it can also be used to compress sort of the binary packed metadata that all this AEC data is going to have. And then for the texture side, this data set doesn't have textures here, or at least this version of it doesn't. But if there are textures, we take advantage of KTX2 and Basis Universal. So in terms of scaling, so this example, the Snowden Towers example, that's a sample project in Revit. It's a 42 megabyte GLB file, but there's often a lot larger models. This is kind of on the smaller side. And we can easily see models that are 500 megabytes plus. So for that, we utilize 3D tiles, and 3D tiles is built on glTF. It provides a spatial subdivision of glTF, and it has a bounding volume hierarchy. So it enables you to stream the data. It also enables level of detail and runtime optimizations like culling. So diving a little bit into the metadata extensions that we've introduced. So the first one on the left is ext mesh features. And that's simply a way to provide this feature ID attribute so you can do sort of the batching. And what it does is this feature ID, it allows you to look into a property table where you might store your metadata. Or if you have an external database with your metadata, you can use that ID to look up into that database. And then ext structural metadata is often paired with ext mesh features. And if you're sort of including metadata in your glTF, this might be a good choice. Essentially what it is, it's an efficient binary encoding for metadata. So if you have sort of thousands of these objects, all with 5 to 20 fields, you want an efficient binary representation of that metadata. And so it consists of really a type system that defines like your integer, floating point, and then string types, Boolean types, enums. There's several different encodings, but in this context, mainly the binary encoding is relevant. And then on top of that, there's an idea of having semantics so that the properties have some meaning associated with them. So you can then say, like, in an application, you can say, hide all the features that or like show me all the features that are doors, hide like the structural elements, like show me the plumbing elements. So that's what the semantic layer provides. And it's what lets us sort of interoperate with IFC or Revit or other data models. So for future work, we're interested in implicit surface representations in glTF. So instead of tessellating all the geometry, it might be nice to store like a CSG or BREP representation, or and especially with like the collision volume extension, that could be a good start to represent sort of the simpler types of shapes. We're also looking to improve the extensions that I just covered to make them a bit more modular, maybe simplify them in some ways, and be able to represent different aspects like class hierarchies and object hierarchies. And finally, we're looking to define sort of a semantic data model that broadly covers AEC so that we don't have a bunch of different data models. And maybe with some like collaboration, we can define sort of a good set for glTF. So with that, I'll hand it over to Adam, and he'll cover Gaussian splatting and voxels.
All right, I'm going to just quickly go through our experimental Gaussian splatting and voxels extensions that we're working on. So with a little bit of data pre-processing, I'm not going to go through this slide detailed. What we found is that we can pretty easily map, if we treat the Gaussian splats as point clouds, we can pretty easily map splat data to glTF data. The big thing is that we're only using the first spherical harmonic, and we're treating that as the diffuse color with the opacity in the alpha channel of that. And so by taking that and just kind of ignoring the other 15 spherical harmonics right now, we've come up with a very rough draft extension for Gaussian splatting. And effectively, we've packed in the rotation and the scale as application attributes. This is probably going to change, just so everybody knows. If you want to download, I don't have a fancy QR code here because it's so experimental, but if you want to download the branch, I do have a link in the slides here. And so one of the things about the way that we've done this, and we've actually got it working in 3D tiles, is that we actually get, with replacement and refinement in 3D tiles, we actually get some level of detail with the splats. And visually, the level of detail actually looks great. You're never close enough to notice any holes on the kind of lower level tiles compared to the higher level ones. So, you know, here's a few images of it actually rendering in Cesium.js, and you can try this out if you want. I'm going to put up instructions soon in the PR. We haven't officially opened that yet, but we will have that open sometime in the next week or so. And the big question that we have for the community here is, you know, where do you want to see Gaussian splats and glTF go, and what use cases do you kind of have for it? That's going to, you know, we're very early in kind of the communication and everything here, so yeah, we're open ears right now. Then finally, in terms of voxels, we're looking to take our experimental voxel extension in 3D tiles and actually bring it into glTF. So that'll be called ext primitive voxels. These aren't OpenVDB voxels, but they are basically kind of a custom voxel format that you know, works very well with glTF. And you can see voxel data that we have from a partner of ours, Camp to Camp, titled as glTF and rendered in Unreal right here. And so the open question that we have for you guys is, what are the use cases where you would get the most use out of this? That's going to help us drive the direction that we go with this. So yeah, thank you.